Let's discuss hardware. To start doing forensic on hardware, the best posture is to follow the pentester's footsteps. This posture will facilitate evidence identification and evidence extraction phases. The first step is recognition. The main goal is to analyze components like labels, manufacturers, versions, analyzing input and outputs, and try to collect as much information as possible from public sources. The internet may know the component as well as you and will help you understand how to discuss it. For example, getting the manufacturer and the version can guide you to getting corresponding datasheets, knowing the correct voltage to avoid frying the board during your investigations. From internet deeper research, maybe some hidden commands will be available and speed up your investigation. A second step of pentester's footsteps is static analysis, where the pentester will attempt to connect to the component and extract information like configuration files or stored secrets. For example, you will try to extract firmware to find hard-coded information, extract binaries or configuration files. The step will help you to understand how the device is working and what it is running. Reviewing binaries configuration files or README will help you to identify weak versions and probably public exploits. The last step is dynamic analysis. At this stage, the pentester will try to do active and passive listening on memory bus. For example, between a system on chip and an external memory like the 24C64 EEPROM, you can put some probes to sniff the traffic and extract sensitive information. In some systems, password or other credentials are stored in those kind of external memories. By sniffing passively, you will be able to extract them. Active will occur when you record some traffic and replay it to the component. For example, if the EEPROM stores coffee credits, by replaying the credit adding request, you basically will be able to drink coffee unlimited. Also, dynamic analysis will allow you to try to manipulate the system through communication ports like UART and debug ports like GTAG. In some devices, you can get a direct serial shell with root privileges. On GTAG, you will be able to live patch the system to bypass some protections. From this methodology, those kind of artifacts can be retrieved. Firstly, if you are finding firmware to do some reverse engineering, you should focus on harvesting in flash or in RAM, dump the firmware, mount all partitions on your systems, and locate sensitive information like credentials. In the case of external storage, like live memory for software, maybe an EEPROM should be identified and easily dumped offline. You can try to put some probes on the chips, or in the case of a QFD mounting sham, for example, try to unsolder it. In the case of the presence of a card slot, you can easily remove it and do all the forensic investigation on the laboratory computer. You can note that some SD cards have an embedded write blocker. Remember to activate it even if you have the forensic dedicated copy device like Tableau hardware. On IoT devices, the display is an interesting sub-device because it is usually operated on I2C or SPI protocols. Understanding pinning combination could allow you to access directly to the bus and sniff the traffic. The specific devices that you should encounter during your investigation are camera and IP cameras if they have internet connection. Taken images of the crime scene should be located on an external SD card or soldered memory. Extraction can be done offline by bridging some probes on the component. Let's talk about interfaces. GTAG is used for component live memory inspection. If this kind of interface is available, do not hesitate to use it. Other input interfaces can be used to explore devices from the console shell or through peripheral like Bluetooth. Some devices will provide voice input like Alexa or positioning functions like the smart bike. All artifacts should be located in external memory like EEPROM or SD storage. It's time for exploration! Woo! During the rest of this part, you will take, as example, an unknown device found at a crime scene. As you can see, the device seems to be a clock. The Bluetooth icon on the top right corner indicates that a Bluetooth connection is available. So let's go analyzing the device and find artifacts. You can make some assumption about this device. Is there a serial connection like UART? Is there live inspection capabilities like GTAG? Is there an I2C or SPI bus for peripheral connections like the screen or Bluetooth? And is Bluetooth embedded in the SOC? Is there other remote control capabilities? You have to explore this. It is time for exploration. We will start by reviewing the physical circuits to find information about the manufacturer or the version. Those elements will help to find additional information from public websites. From the provided picture of the device and after removal of the screen, we can see that the system on the chip is an Atmega 328P. This information is useful for looking for datasheets, download, and getting information about the standard UART communication port. At the bottom, there is also an extension port named BLE. It means that the board provides a Bluetooth connection. At the rear, you can see the name Damn Vulnerable IoT Device. This object is in version 1.0 from April 2019 and is under GNU GPL licensing. The designer is Vulkan. You can, right now, try to Google all the information. You will probably find that Vulkan is me, and the board is part of the Damn Vulnerable IoT Device open source project. You will also probably find that all schematics are available to download and will be precious to help during reverse engineering. Don't hesitate to write down in a notebook all your findings. They will be useful for the future work. Based on all previous information, like observations and datasheets, websites, and community work, it's time to make a Shimmer. The Shimmer will help you to understand what the pinning configuration is, how to interact with the board, and what kind of tool you need to bring with you. Firstly, place the sock in the center and label the major identified pins. Here we can start by powering up with VCC and ground and the UART connection with the reset pin, RX pin, and TX pin. The next step is to write down the connection between the Atmega 328P and the Bluetooth low energy device. Place the Bluetooth device and the corresponding pinout. From track following directly on the PCB, you can write down the connection between the Bluetooth peripheral and the sock. Do you think it's enough? By exploring the datasheet, you can see that you will be able to dump the Atmega 328P, flash and embedded EEPROM. The connection of the dumping tool is not made by the UART connection, but with SPI pinout. You can also write down pinouts to help you find a damping way. About tooling, you will need to bring a UART dongle and an USPASP flasher. Don't worry, they are already provided in your DVID kit. The second demonstration is about firmware exploration, dumping, and exploitation. For example, on the manufacturer's website, you should download the device firmware. Don't hesitate to brute force the domain name or Google it to find the correct name, but first try support.manufacturerofficialwebsite.com. After downloading firmware binaries, the tool binwalk can help you to extract the contents. Also, the Linux command find associated with filename shadow will allow you to automatically locate sensitive information and extract it. If every command is run successfully, you will probably find a default login, corresponding passwords, and if you're lucky enough, it could be the root password of the device. The second demonstration is about our clock firmware dump. The command avr-dude can help you to extract the firmware. From the firmware, you can search for useful strings, like one containing the string pass, and if you're lucky, again, it could be the password used in pairing or local data encryption. The third demonstration is about sniffing the BLE. This method will be useful to understand what is transmitted into wires during device running. Helped by a probe, you can attach a UART dongle to the TX and RX of the Bluetooth peripheral. You should better understand why the information gathering phase is so important. By reviewing the DVID GitHub project, you have probably found that the Bluetooth device is connected using UART connection. The TX and RX pin are connected crossly between the Atmega and the Bluetooth dongle. After a correct probe installation and opening a serial monitor, you will see, as shown in the screenshot, some data on the BLE peripheral. This is, sadly, the end of the hardware part. You can replay all those demonstrations from the training part, and please go ahead.